Hello everyone and welcome to a new lecture. In this video we are going to talk about Euler and Fermat theorem. So in the previous lectures we talked about both of these theorems. We talked about Euler's totem function, or phi, that counts how many totatives a particular positive integer has, and then we talked about Fermat's theorem, which says a to the p is congruent to a mod p. So Fermat came up with his theorem in around 1640. However, he did not prove it, and it took almost 100 years for Euler to come and then prove his theorem. And then what Euler did is to extend Fermat's theorem, which says a to the p is congruent to a mod p, to include his phi function, or to include Euler's totem function, to create this relationship saying that a phi of n is congruent to 1 mod n when a and n are coprimes. And as it turns out, this particular relationship is very important, especially in sending messages securely or in cryptography. And I'll tell you some other use of it when we try to find modular exponentiation. So let me give you an example on a to the phi of n is congruent to 1 mod n, or on Euler and Fermat's theorem. So suppose we have n equaling to 3 and a equaling to 4. Then, as you can see it, n and a are coprimes, or 3 and 4 are coprimes. So a to the phi of n, phi of 3 are 1 and 2. So 4 to the 2 mod 3, 4 to the 2 is 16. 16 mod 3 actually is 1. So as you can see it, a to the phi of n is congruent to 1 mod n when a is equal to 4 and n is equal to 3. So suppose we have n equaling to 6 and a equaling to 5. The totatives of 6 are 2. They are 1 and 5. So as you can see it, phi of n, or phi of 6, equals to 2. 5 squared mod 6, 5 squared is 25. 25 mod 6 equals to 1. So a to the phi of n is congruent to 1 mod n when n equals to 6 and a equals to 5. So basically, this is Euler and Fermat's theorem. So let me show you how you can use Fermat and Euler's theorem in order to do problems in modular exponentiations. So suppose we have this that says, what is 7 to the 222 mod 10? So suppose we have this. How can we use this relationship in order to solve this problem very quickly? If you notice, 7 and 10 are coprimes, and that's a good sign. So how can we use it? Well, 7 to the phi of n is congruent to 1 mod n. So phi of 10 actually equals to 4. So 7 to the 4 is congruent to 1 mod 10. So when we have this, we will use this equation in the problem. How can we use it? Well, let's make this 7 to the 222 mod 10 into little powers. So let's turn it into something like this. 7 to the 4 times 55 plus 2 actually equals to 222. So we will make it like this. So we can say, or 7 to the 4 times 55 plus 2 mod 10 is equal to 7 to the 4 brackets 55 times 7 to the 2 mod 10. So as you can see it here, I have 7 to the 4, and I know that 7 to the 4 mod 10 is congruent to 1. So I can just say this is 1 to the 55 times 7 to the 2 mod 10. And 1 to the 55 is just 1, so I just have 7 to the 2 mod 10. 7 to the 2 is 49, and 49 mod 10 actually equals to 9. So as you can see it, if I use Euler and Fermat's theorem in modular exponentiation, my problem becomes very easy. And with this, we come to the end of this lecture.